consider a band with anisotropic dispersion relation. So we have been given a anisotropic. Why anisotropic? Because if you see kx, if we see in the k space, kx, ky, and kz. So for a given energy means uh, so imagine a surface with constant energy. Okay, if you draw that in this kx, ky, kz space, it will be something like an ellipse. Ellipse means the distance at which kx will this ellipsoid will intersect kx, ky. So at this point, and this point, this need not be same. Okay, and this need not be same. So that happens for cases where the material is anisotropic. Anisotropy means in all in different directions there will be no symmetry. So along a particular direction there will be some different spacing of the lattice spacing, and in other direction there will be some different lattice spacing. In those type of materials it will happen. So now so it has given the fact that what is the volume of an ellipsoid. So volume of an ellipsoid, it is given 4 pi by 3 ABC. We have to find what is the density of states. Okay, so if you remember the way we derived for the isotropic case, in which mx, my, mz was the same. So so mx, my, mz was same, then we could have taken this mx, my, mz common and taken it out. So it will be h bar square by 2m into k square. But now it is the different case. So in that case, the density of states, how we used to find? We used to find, so density of state is number of states G of A is equal to number of states per unit volume per unit energy range, or it is the number of states per unit volume between energies E to E plus dE. So if we take two different energy cells, okay, so the energy of this is E and energy of this is E plus dE. Then what are the number of states which are available in this particular cell? That will give me the number of states. So this number of k space, and we have to multiply it by 2 for the spin, because there would be 2 spin up and down. So we have to find what is the number of these dots, or this what is the number of this k points. So we know that every k point, so every state along it will give a contribution of every state will have a contribution of 2 pi over L by 2 pi. So let us say that the volume. Okay. So what we have to do is, so if we want to find what is the k space volume of one particular state, similarly ny equal to ly ky over 2 pi, and nz is equal to lz. This thing is clear, right? That this is how the states are counted. Okay, and we have to what we want to do is what we want to find the k space volume of volume in k space for one k state. So it will, so what we want is this delta n x, delta n y, delta n z, this should be 1. Okay, and this will be 1 if we have, so del lx delta k x by 2 pi, ly delta k y by 2 pi, and lz delta k z by 2 pi. So delta kx, delta ky, delta kz. So this means this is the k space volume for one k state. So it will be 2 pi whole cube over lx, ly, lz, or 2 pi whole cube divided by the volume of the material. Okay, so this is the volume in k space for one k state. Okay, now how can we find what is the number of dots or the number of k states in this cell? So we have to find what is the volume of this particular cell, ellipsoidal cell, divided by the volume of one k state. That will give me the number of k state in this particular cell. So let us just find that. So this is E, and this is another cell at E plus DE, and we want to find what is the number of k states in it. What is the number of k states in it? We already have seen that delta kx, delta ky, delta kz is equal to 2 pi whole cube over volume. This is for one state. K space volume of one state. Okay. Now what we want to find is the volume between these two. So what we can do is so we have to use this information now. So we have been told that if, so this is the equation of an ellipsoid. So here, okay, this is kx, ky, and kz. So we are given this particular volume. So kx by a whole square plus y by b whole square plus z by c whole square is equal to 1. This is the if this is the ellipsoid, then the volume will be given by 4 pi by 3 a, b, c. So for this ellipsoid, what would be this a, b, and c, that we have to find out, and that we can get from the dispersion relation. So the dispersion relation is given by, so this is our dispersion relation, energy, or the energy is given by h bar square by 2 kx square by mx plus ky square by my plus kz square by mz. Okay, so this we want to write it as this particular form. So we divide everything by energy. So it will be kx square by 2mx energy by h bar square, and so we want to write as that form. So what we will do is whole square. Similarly, ky by square root under 2my h bar square whole square plus kz square 2mz h bar square whole square. Okay, so the volume of k space volume of the ellipsoid, okay, of the ellipsoid with maximum energy epsilon, it will be given by of the ellipsoid is given 4 pi by 3 ABC. Now our ABC is the denominator of x, y and z. Here it will be the denominator of kx, ky and kz. So it would be 2 uh, 2mx by h bar square 1 by 2 2my h bar square 1 by 2 2mz by h bar square to the power 1 by 2. This is how it will be. Uh, but now what we have to do, we have to find, so basically the strategy would be, so at E, so this is ellipsoid at E, and what we want to find is what is the number of states between these two. So we want to find k space volume. So what I will write it as the volume in k space at energy E. Okay, of I'll write denominator k because it is in the k space, or we can write this omega is where omega is the k space volume. K space volume between E and E plus dE. So this will be given by just d omega by dE. Okay, it's d. So this will be your k space volume between these two. So what we will have is, so this is, so we'll put all the constants together, 2 pi 4 pi by 3 so 4 pi by 3 and it is 2 root 2 over h bar cube, and it is mx and y mz 1 by 2 3 by 2, and we have to do the derivative with respect to energy. So this will give me 4 pi by 3 2 root 2 by h bar cube mx and y and z 1 by 2 3 by 2. Okay, so this is the k space volume between k space volume between E and E plus dE. Okay, so this is d omega by dE into dE. Now what we want to do is we want to find the number of the number of these points. So we have to divide the number of k states will be this quantity divided by the k space volume of one state. Okay, so now all we need is we have to divide this quantity by this quantity. So what we have is the number of k states between E and E plus dE is equal to d omega by d over. So this is the k state for k space volume of one state, one k state, and this is the k space volume of ellipsoidal cell. Okay, so we just have to evaluate this quantity. So what we have is from previous slide 4 pi by 3 4 pi by 3 2 root 2 So that was the numerator, and the denominator would be 2 pi whole cube over v. Okay, so this is the number of k states. Now the number of states between E and E plus dE. So here we have to multiply another factor due to spin. Okay, so this was the number of k state. For each k state you have to we have two spin states, so that is why you have to multiply by this 2. Okay, so now number of states per unit volume between E and E plus dE. So since it is per unit volume, we have to divide by this volume now. So it will be 2 4 pi by 3 2 root 2 by h bar cube, and this is 3 by 2 mx my mz 1 by 2 over 2 pi whole cube. Okay, so we have to find, so the question was asking about what is the density of states. So the density of state is defined by like this: number of states per unit volume per unit energy range. So it is so what we have to do is we have to now divide by the energy range. So what is the energy range? Energy range is just dE. Okay, so what we have to do, the number of states per unit volume per unit energy range. So it is just, so we just have to divide by dE. So if you just take that factor out, so you will be left with this 4 pi by 3 2 root 2 over h bar cube 3 by 2 mx my mz this to the power 1 by 2. Now it is just a matter of simplification. So this is nothing but your definition of density of states.